Hi everyone, I hope you're doing really well. I just wanted to come to you today with a little video just about, hope we're still going here. There we go. About gas laws. So, like you must have noticed from yesterday's reading, we're starting our Unit 8, which is on gas laws. And so today is just about an introduction to gases, should cover some of the material you read about yesterday. Now, what's interesting about our gas laws unit is it's one of my favorite units to cover actually, because like I mentioned in yesterday's video, it actually applies to our life in so many different ways. When we boil something, that's related to gas laws. When we use a straw, that's related to gas laws. When we pick up a can, that's related to gas laws. So there's so many cool things that I'm going to be able to show you and teach you about that are actually applicable to our everyday life. And so normally this, like it does this year, comes up in fourth quarter, and I really like that because I like to end the school year with connections to our everyday life. Like, why do we care about studying chemistry? It's to understand the world around us. And so obviously I want to show you guys some connections to that. So we're going to do our gas laws unit, which is great. So hopefully you know some stuff about gases already. Normally when I ask this question in class, what do you know about gases? People say things like, we sometimes can't see them, sometimes they smell, sometimes they don't. So they sometimes have an odor, sometimes they're odorless, and so forth. So you guys are a little bit familiar with gas. The study of gases actually started over 300 years ago, when scientists decided to study air, which is what they thought to be the most common gas. They were unaware of the fact that at that time, air is actually a mixture of different gases. I said that a little bit incorrectly. At that time, they were unaware that air is actually a mixture of several different gases. So I don't know if you guys know what's in air. I'm sure you all know that there's oxygen in air. But in addition to oxygen, there's carbon dioxide, which is what we breathe out. There's a little bit of argon. There's some nitrogen. So there's a bunch of different things in our air, a bunch of different gases in our air. But what scientists did is they studied air as if it were a single gas. But they realized, and they had this then important discovery here, led to an important discovery, that even though air is a mixture of gases, it actually just behaves like a single gas. And so that was really critical because what scientists realized about 200 years ago is that regardless of chemical identity, all gases exhibit similar behavior. So it doesn't matter whether we're talking about carbon dioxide or oxygen or nitrogen or argon or carbon monoxide, all gases exhibit similar behavior regardless of their identity. Now, that doesn't mean all gases are the same. For example, carbon dioxide, which is a gas that we breathe out, right? We breathe in oxygen, we breathe out carbon dioxide, is obviously safe for us. But carbon monoxide, which is the gas that comes from the tailpipe of a car, for example, is toxic to us. It would actually kill us. It's a poisonous gas. We have carbon monoxide detectors in our houses and in our school and so forth to make sure that we don't have too much carbon monoxide because it is unhealthy. So saying that regardless of chemical identity, all gases exhibit similar behavior doesn't mean all gases are the same. What that means is when I heat up carbon dioxide, it takes up more space. When I heat up carbon monoxide, it also takes up more space. When I cool down carbon dioxide, it takes up less space. When I cool down carbon monoxide, it takes up less space. So it's not that all gases are the same. It's just that all gases respond to outside forces in the same way. And so that's what we mean when we say all gases exhibit similar behavior. Now, this means that we can use a set of laws to describe all gases, hence our gas law unit. You'll notice that before I say that, you already know one example of this. Remember when we did our stoichiometry unit, those of us who did that with me when we were on our Act of God days, we learned to use 22.4 liters per mole. Okay, and that was one example of when we could use the same number for every single gas, no matter what gas we talked about. Now, if you didn't do our stoichiometry unit with us, no big deal. You'll still be fine in the gas laws unit here. Oops, struggling with my new pen here. Let's see what's happening. There we go. I was trying to do that. Okay, so 22.4 is just an example of gases being similar to each other. Now, what's interesting is we can't do the same for solids or liquids. So we don't have a unit called solid laws or liquid laws because all solids and liquids really behave differently depending on their identity. So for example, water and alcohol don't behave the same when I heat them both. Those are two liquids that don't behave the same. Imagine different solids. For example, a solid piece of iron and a solid piece of dry ice don't behave the same at all. So we don't have any unit called solid laws or liquid laws, but gases do all behave very similarly. So what are some properties that are common to all gases? Number one, gases have mass. Okay, this is something most people don't realize because air is a gas and people feel like, oh, I don't feel the air touching me at all. Well, that's just because our bodies are used to it, right? Gases do in fact have mass, and we could come up with a very simple experiment. We take a basketball deflated, we put it on a scale, we measure the mass, then we fill it up, put it on the scale and measure the mass again, and it will actually weigh more. So we know that gases do have mass, even though we don't always detect that mass ourselves. Like we might not feel it, right? Right now, oxygen is hitting my body and I don't feel that mass, but that doesn't mean it doesn't exist. Okay. Gases are easy to compress. Compress means squeeze into a smaller space. So imagine if I have some kind of piston, it's like a syringe, okay? And there's some gas in here. If I push down on this piston, I could get this gas to compress, to take up less space, right? Maybe it used to be like this. And if I draw it again here, if I draw it again here, I could get it to take up this much space, right? I can compress gases, and gases are easy to compress. Now, why are gases easy to compress? It's important to be able to understand that. Let's just think back at this picture. This is what a solid looks like at the particulate level, at the atomic level, right? All the atoms are neatly organized and tightly packed in. This is what a liquid looks like. The atoms are tightly packed in, but not as ordered, and there's a little bit of movement. And then this is what a gas looks like. The particles are super far apart from each other, and there's a lot of movement of these particles. And so if I compress a solid, you can see there's no space for the atoms to move. They're already as tightly packed as possible. If I compress a liquid, okay, I might be able to change the shape of the liquid a little bit, but they're already touching these molecules or these atoms. So again, it can't get up to take up less space. But if I compress a gas, you can see that there's a lot of space in between each of these molecules. And so if I push them together, I could actually get them to take up less space. And that's what it means when we say gases are easy to compress. Okay, an example of gases being easy to compress is when air is used as an absorber in airbags. So imagine in a car if an airbag popped out and your face just went into the airbag, but the airbag didn't actually push in, it didn't compress. If that happened, that would actually hurt quite a bit, and we wouldn't be using airbags. But because gases are easy to compress, when your face hits the airbag, you can actually push on that bag, the air gets compressed, and it protects you. Okay. Gases fill their container completely. So that's an important property of gases. If I just, let's say, put in 2 little atoms of gas in this big container, it's not like these two atoms are going to stay down here the whole time, right? Because gas particles are constantly moving, actually, those gas particles are just going to whiz around this container and go wherever they want all the time. So in terms of volume, the volume of the gas is always the volume of the container because gas particles are constantly moving. That's unlike a solid. Let's say I put two solid atoms on there. They don't have any movement. They're just going to take up this tiny amount of space right here. Okay. Gas particles are constantly moving, which is important to know. Okay. Because they're constantly moving, different gases can move through each other rapidly. This is called diffusion. Okay. Diffusion is movement of one substance through another. To just understand diffusion, you guys have all seen diffusion. If you can imagine a glass of water, okay, and then you put one drop of food coloring in that water and you don't touch it. If you look at that water 5 minutes later, you can see that the color has diffused through and now it's spread evenly throughout the water. That's what diffusion is. One substance moving through another substance. And if you sit there and watch it, you can actually see the diffusion happen. Imagine a drop of red food coloring. It's concentrated where the drop is, and then you can slowly watch those lines come out, and it kind of spread everywhere until you have a light pink water. So that's what diffusion is. Now, what's special about gases is they diffuse really, really quickly. Okay, they can actually move really quickly. I always talk about the air freshener industry when it comes to diffusion. All air fresheners are based on this idea that we can get nice smelling stuff to diffuse through the air to make it smell better. So if you think about different types of air freshener, one example is a solid air freshener. That would be like one of those gels that you buy. And you just open it up and put it like on a desk or something. Okay, imagine I brought one of those. We're sitting in our classroom. I brought one of those. Dorian's in the back corner of the classroom, okay, as far away from me as possible. If I open up one of those gels, how long would it take before he could smell it? Probably not during the class period, right? I would maybe smell it in a couple minutes. Maybe the people closest to me would get some wafts of it. But really, if Dorian is as far away as he could be in the classroom from me, he's probably not going to smell that gel that I just opened on my desk. On the flip side, if I use something that comes out in gas form, like an aerosol can of air freshener, you know, the kind that goes shh when you press it. Imagine I started doing that. I'm at my desk. Dorian is in the back corner as far away from me. I go shh. How long before he smells it? Probably only 10 or 15 seconds, because what's coming out of that aerosol can is a gas, and gases diffuse quickly. So those gas particles actually move really quickly and get all the way to Dorian. So the air freshener industry is really based on these properties of gases. Now, why then does anybody want that gel one? Well, it really depends on what you're doing, right? If, let's say someone's coming, my house smells terrible, someone's coming over in 2 minutes, I'm probably going to use the air freshener and get that to smell really good for a couple of minutes very quickly. But what happens if I'm having people over for several hours and I just want something to smell kind of nice the whole time they're there? Then I might choose to use a solid air freshener that's going to not be as strong, but maybe last a little bit longer. Because the thing with gases diffusing quickly, yeah, I can get it to smell good quickly, but that nice smell is going to go away quickly as well, right? So it's really interesting to think about that. Also, of course, I don't know if you guys have ever seen those like liquid diffusers, the ones where it's like a bottle of nice smelling liquid and you put those sticks in it. Okay, that's something in between. It's not going to be as slow as the solid one, but it's also not going to be as fast as the aerosol one. So all that to say, gases can move through each other rapidly. Gases can diffuse rapidly. Okay, gases exert pressure. The biggest example of this is a balloon. Why does a balloon hold its shape? Well, it's because, I don't know why that line keeps coming. It's super annoying to me. Basically, that's supposed to be a balloon. I'm like terrible at drawing. You guys know that about me. Let me try something better here. Maybe that looks more like a balloon. Okay, this is a balloon, and this is the gas inside of the balloon. And the reason the balloon holds its shape is because these gas particles exert pressure on the walls of the balloon. And so that's why a balloon holds its shape. So we know that gases exert pressure, okay? The other way you know that gases exert pressure is when your ears pop. If you've ever been in an airplane or an elevator and you get that sensation of your ear popping, or sometimes you just even have a bad cold and your ears are hurting, that's because the air inside your eardrum is exerting pressure on your ears. And so we know that gases exert pressure. That being said, we also know that our atmosphere is made up of gases. So right now, wherever you're sitting, gases are actually exerting pressure on you. You don't necessarily feel that pressure, but the gases of the atmosphere are exerting pressure on you. Okay. And then the last piece is that the pressure of gas depends on temperature. As temperature goes up, pressure goes up, and as temperature goes down, pressure goes down. So an example, and I think we've talked about this example before, is a helium balloon in winter or in summer. So imagine it's the dead of winter. I go into Party City, I buy a balloon, I come outside, I look up, my balloon looks deflated. I'm like really upset about it. So I go back into Party City and I say, hey, my balloon is deflated. I look up and the balloon is fine. Well, what happens there? What happens is that the temperature actually causes the gas particles. Remember, this is my balloon and there are gas particles in it. And those gas particles push against the walls of the container. And that's why the balloon looks good. But when I go out into the freezing cold, these gas particles actually start to move super slowly. And if they move super slowly, they don't hit the walls of the balloon as often. And then it starts to look deflated. It's not that the helium went out of the balloon. It's just that the balloon looks deflated because the helium isn't hitting the edges of the container. And so I think I have to try to switch pens. Let me do that. As the temperature goes down, the pressure goes down, and then the balloon looks deflated. I walk back into Party City and say, hey, my balloon is deflated. And suddenly we're back to room temperature. So the walls of the container are getting hit by these particles and everything is fine. So temperature really affects the pressure of a gas. Now, alternatively, let's say I bought my balloon for 4th of July and it was 100 degrees outside. I throw the balloon in the car. I go into Jewel to grab some groceries. I come out and my balloon has popped. Well, in that situation, it's like the opposite. There were particles in here. They were hitting the balloon. Suddenly it got super, super hot. And because it got super, super hot, the particles started moving crazy, kept hitting the walls of the container to the point where it actually busted the balloon. Okay? So to explain all of these observations, like scientists studied gases and they realized that all of these things that we just talked about, scientists came up with something called the kinetic molecular theory, or the KMT. So I'm going to actually stop the video here for now. And then tomorrow we can talk a little bit more about the kinetic molecular theory. But as you go along today, try to think about where you're observing gases in your everyday life. And are you observing, or at least like coming into contact with some of these things that we talk about? The fact that the pressure of a gas depends on temperature, that gases can diffuse, that gases exert pressure, that gases have mass, that gases fill their container. One last thing I want to gas is easy to compress. One last thing I want to talk about is something that students often get confused about. Remember that gas that we put into our car is actually gasoline, and that is actually a liquid. I want to stop right here. So one common mistake my students make when they're thinking about properties of gases is they envision themselves like at the gas station pumping gas into a car. So we use the word gas for that, but that is actually gasoline, which is a liquid. So it's a little misleading. When we're talking about gas laws and gases being easy to compress and all of that, that wouldn't apply to the gasoline that we put in our car because gasoline is actually a liquid. So instead, you want to think about gases as in something in the gas space. So just make sure you keep that in mind. All right, hopefully you guys are doing great. Can't wait to talk to you more. And soon we will have learned enough about gases that I can start recording some cool demos here at home for you. All right, have a great day, you guys. Bye.